Welcome to the first lesson on gas laws. We're first going to talk about the basic gas laws, and then we're going to go into the ideal gas law. So before we do that, we need to talk about some basics of gases, how we are going to describe their behavior. So let's start with the kinetic molecular theory of gases. The kinetic molecular theory applies to all particles of solids, liquids, and gases. And if you remember from first semester, it says that the particles of all matter are always in motion. Remember, solids are, the particles are just vibrating in place. In liquids, the particles can slide past one another. But in gases, they have some very different behaviors. So let's talk about number one. We're going to talk about ideal gases versus real gases. And basically what an ideal gas is it's like if the whole world was perfect and behaved perfectly, this is how an ideal gas would behave. But in actuality, they don't exist. It's kind of like pretend. But we have to talk about how the theory of ideal gases applies and how real gases differ. And so the first component of the molecular theory is, sometimes we call it KMT for short, so you might see that, KMT. Number one says the particles in an ideal gas have no volume, and the particles are very far apart. And in an actual real gas, they actually do have volume, and so some of our calculations are going to involve volume. The second postulate says that particles in an ideal gas move in a straight line motion, straight line path, and random directions. And that is true for both real gases and ideal gases. They are moving very random, but they're not zigzaggy, curvy. They are in a straight line. Number three says particles in an ideal gas collide frequently with each other. Collide frequently with the sides of the container, but less frequently with each other. All collisions are elastic. And basically what an elastic collision is that when the particles collide, no energy is gained or lost as a result of the collisions. However, in a real gas, the particles do lose energy when they collide. Number four states that particles in an ideal gas do not attract or repel one another. In other words, there are no intermolecular forces. Remember, we talked about that back in the bonding unit, where there's an attraction for each other on the particles. And in an ideal gas, ideally there's no attraction. However, in a real gas, they do have an attraction for each other. And they can have intermolecular forces. That's quite frankly how we were able to get like liquid nitrogen and liquid argon, because there is some attraction for each other. And number five says the average kinetic energy of both, now this is for both the ideal gas and the real gas, is proportional to the temperature of the gas. So if the temperature increases, the kinetic energy increases. Okay, so that is directly proportional. If one goes up, the average kinetic energy goes up, that means the temperature is going up. But if you increase the temperature, the particles move faster and they increase their kinetic energy. So what does this mean for us? It means a couple of things. First of all, in theory, ideal gases cannot form liquids and solids, but real gases can at lower temperatures. And the reason they can at lower temperatures is the particles aren't moving as fast, and so they can have a better chance of being attracted to each other because they're moving slower. Under conditions of high temperature and low pressure, real gases can approach ideal gas behavior. Okay, and that's because basically at these conditions the particles are very far apart. And so when the particles are far apart, that means there's less attraction for them to be able to form, and they behave more like an ideal gas. Also nonpolar gases, because they don't have attractive forces. Well, actually they do. They have those London dispersion forces that are very, very weak. So the four variables used to describe gases, the first one is going to be volume, and it's going to be with a big V, and then it's usually going to be in liters or milliliters. But I want to caution you that if you have one in liters and one in milliliters, you have to be in the same unit. So I'm going to remind you that in 1,000 milliliters are in 1 liter. Pressure can be measured in torr, atmosphere, millimeters of mercury, or kilopascal. Atmosphere is the most common that we'll use, and these are the conversion factors, so you will need to use this. And you do have a worksheet that we are just going to practice pressure conversions on, so you can make sure you have that down because you'll need to use that. 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 101.3 kilopascals is what that unit is. Notice that these are equal to each other, okay? Basically, the millimeters of mercury is very common, and they wanted to honor the man who invented the barometer. And the barometer, you might want to write that down, a barometer measures pressure, and his name was Torricelli, and they wanted to give him the honor of calling it a torr, just to give him that honor. Next thing is Kelvin temperature. Temperature is the other one, big T. Always are going to use Kelvin in gas laws. I cannot stress this enough how important that is. If you work these gas law problems in Celsius temperature, they will not work. You'll get a wrong answer every time. And at the very beginning of the year, I told you this is the easiest conversion in chemistry. You take your Celsius temperature and you add 273 to it, and that is it. And then the amount is going to be a little n, and it is going to be measured in moles. I told you the mole never goes away, okay? Something we need to be aware of is when we're talking about gas laws is it can be at standard temperature and pressure. And standard and temperature and pressure is going to be 0 degrees Celsius or 273 K, and standard pressure is going to be 1 atmosphere. Also could be 760 millimeters of mercury or torr, and then 101.3 kilopascal. And so what's going to happen is you'll see a problem and it'll say, oh, the conditions were changed to standard temperature and pressure, and you'll think, oh my gosh, I can't work this problem, I don't have enough information. Yes, you do. They expect you to know that standard temperature is 0 degrees or 273 K, and they expect you to know that the standard pressure is 1 atmosphere or one of those other conversions, okay? So that is very important for you to know. We're going to stop this first lesson here because I believe you have a worksheet on pressure conversions, and I want you to do that, and that does need to be entered into Canvas. You'll just enter your answers into Canvas, okay? That's the end.